In the previous video, we have seen some applications of the Laplace transform. Now, I would like to look at its properties. First is a property we have actually under the hood been using in the previous video, is a linearity property. That means that you can shift a constant inside and out of the Laplace transform, and the Laplace transform of a sum is the sum of the Laplace transforms. It follows by distributivity of product and linearity of integrals. What do I mean by that? Is that if you do the Laplace transform of AU plus BV, well, you can easily distribute the product of E times ST on the first and on the second term, and you can take out of the integral A and B. So we easily retrieve the property. Let's also look at properties involving the derivative of a function. So the Laplace transform of a derivative is equal to S times the Laplace transform of the function minus the function computed at 0. We're going to prove this as well. So let's look at the Laplace transform of the derivative of f. Then it's the indefinite integral from 0 to infinity of f prime e at the minus st. By integration by parts, we can take out of the integral f of t e at the minus st between 0 and infinity. We can take out of the integral s, and we are left with exactly the formula. The first term disappears at infinity because of the exponential, and the second term is exactly s times the Laplace transform of f. Let's apply this formula in a couple of interesting cases. Let's look at the first example. This is t at the n. We know its derivative quite straightforwardly. So the Laplace transform of the derivative of f, we can take n out of the Laplace because of linearity. And then we can use the formula, the property of the derivative, to write on the right-hand side that is equal to s times f of t, where f of t is t to the n. f0 in this case is 0, so we don't have to care about that. And with some mild reshuffling, we see that the Laplace transform of t to the n is equal to n over s, the Laplace transform of t n minus 1. That is what we have found previously, and that can be used as a recursive formula to find the Laplace transform of t to the n. Let's look at a second example. What might it be? The cosine and the sine. So we have here the sine is f of t, and a cos is the derivative. By definition of the Laplace transform of f prime, we have that it is equal to a times L cos at. By the property of the derivative, we also know that it has to be s times L sine of at. I'm sorry for the mistake in the slides. Let's then put it all together. Then we know that the Laplace transform of the sine is a times s, the Laplace transform of the cosine. That is indicatively what we have found in the previous video.